Hello, good morning, everyone. Um, what we have studied in the previous lecture is a Pelton wheel, which is basically a high head impulse turbine. Today, we'll be moving on to the other two types of turbines, namely Francis turbine and Kaplan turbine. Both of them are classified under a reaction turbine. This is a Francis turbine. Even though we say that Francis turbine and Kaplan turbine are reaction turbine, they are not completely reaction turbines. There will be a combination of an impulsive force as well as a reactive force. Now, what we are seeing is the front view of a Francis turbine. This is important because later on, when we see a Kaplan turbine, which resembles exactly this sketch approximately, um, that is going to be the top view, which means that if this is the front view, the axis of rotation of the shaft of a Francis turbine is horizontal, while in case of a Kaplan turbine, it is so mounted that the axis of rotation will be vertical. This represents the penstock through which water is going to come into the turbine, and the casing, the outer one, this entire thing is called as the casing, the which is mentioned as spiral. Now, in some books or sometimes we also refer the shape of the casing as also an involute casing. Now, the reason why it is called a spiral casing is because if you see the shape carefully, the gap between the central circumferential wheel, this is the central circumferential wheel, and the casing is more here, and as you progress, it reduces. This is only to ensure that the whole casing is filled with water. Suppose if the casing and the circumferential wheel are concentric to each other, it may so happen that all the water which is entering through the turbine will flow into the blades here only, and here there will be absolutely no water at all, which will create a kind of cavitation, or it may lead to a void. Okay. Now, this is the central part, which is actually the rotary part, this one, and it has got vanes. You can see there are curved blades on it. They are called as the vanes on which the water is going to flow. There is another wheel which is called as a guide wheel, and on the guide wheel you have what are known as guide blades. Now, the guide wheel and the guide blades are stationary. What I mean by stationary is there is a small motion, small rotary motion which can be given to it, but it does not rotate completely as compared to the central circumferential wheel. So the central circumferential wheel is called, or it has what are known as the runner blades. You can see that it's mentioned here as runner blades. Now, what is the purpose of this guide wheel and guide blades which are mounted together is that they are mainly used to regulate the amount of water flowing into the runner blade or over the runner blades. So, for example, now in the current position, maximum amount of water will be flowing through the runner into the runner blades. Suppose I turn the guide wheel by a very small amount in this direction, then it will so happen that these guide blades will slightly get lifted, and the gap between two guide blades is reduced, which will reduce the amount of water flowing into the runner blade. So once the water flows over the runner blades, the blades are so shaped that when water flows through or over these runner blades, there is going to be a reactive force. And since the reactive force will be similar on all the runner blades, the the runner wheel on which these blades are mounted is going to rotate in a particular direction, let's say anti-clockwise, and that will make the shaft also rotate in the same direction. So this is what we call as the circumferential inlet and axial outlet. The water flows out along the axis, and unlike in a Pelton wheel where the water was directly discharged into the tail race, it just fell into the tail race and it was taken away. Here you have a special outlet pipe which is called as a draft tube. Okay, so you can see that there is a conical shaped draft tube, um, and it is diverging in shape. Now, there is another reason why the draft tube is conically shaped and why it is diverging. Why is it not straight like this? The reason is when the water is getting discharged, there has to be a reduction in pressure so that water will also continuously get sucked into the runner blades. No doubt, the water is coming with a great force here, but water should also, to some extent, get sucked between these spaces into the runner blades. So that is the working of a Francis turbine. Again, as I said, there is an animated video which I will post it in the group later on. You can see how exactly it works. So this is the working. It is a medium head reaction turbine where water flows radially inwards and axially outwards. So it consists of spiral casing, and there is a number of stationary guide blades, which was just discussed, and there are vanes which form which are mounted on the runner. So water at a high pressure enters through the inlet, and it flows radially inwards to the on through the runner blades in between the guide blades. From the outer periphery, the water flows inwards, and whatever energy is contained by the water, both velocity and the pressure energy, there will be a combined effect because of which the vanes start rotating. Because the vane rotates, the shaft also rotates. Now, this is what I was discussing. That is the amount of water entering. This point is very important. The amount of water entering the running vanes is controlled by a circumferential wheel fitted with the guide blades. And the discharge of water at a lower pressure takes place through a diverging conical tube, which is called as the draft tube. The name of that is the draft tube. Now, to ensure that this suction is always maintained, that is, differential pressure is always maintained, the draft tube should always be immersed in a water bath, that is, in the tail race, and that tail race should also contain water in it. So this is the working. Obviously, what will happen is, once it starts rotating, this shaft is going to be coupled with the shaft of a generator, and electricity is going to be produced. Then we have a Kaplan turbine. See, if you see the sketch of a Kaplan turbine, this very much resembles the sketch or the pictorial representation of a Francis turbine. However, here it is clearly mentioned that it is the top view. You can see that it is the top view. In the previous section, when we studied the Francis turbine, that was the front view. So, which means when you see a Kaplan turbine from the top, it looks like this, which means this is the axis, and the axis of a Kaplan turbine is vertical. Rest all is almost the same. The constructional features are almost the same. The main difference will be that it is a vertical axis turbine, and the shape of the runner is slightly different in this case. So the various parts are shown in this. So this, for example, represents the runner. So this whole thing represents the runner, and it resembles the propeller of a ship. Okay, so hence Kaplan turbine sometimes is also called as a propeller turbine. So these are the blades or the vanes. You can see the vanes which are mounted on this. So the water enters. This is the shaft which is whose axis is vertical. So the water enters and it flows over these vanes. So when it is flowing over the vanes, because there is a change of direction, there will be a change of momentum, and there is a reactive force which is going to be exerted on these vanes, which will make it rotate on all these vanes. So finally, this will start rotating in the anti-clockwise direction like this, because there is a backward force which is going to be exerted. So this is the main component, that is the propeller of a Kaplan turbine. Here you can see there is a small difference in the casing also. So the casing, of course, is again spiral, there is no doubt, but the size, this is the size of the casing, and as it moves, this is slightly bigger than this one. So water enters through these veins, it flows over this, and it is again discharged through the tail race. Now there is a small difference. We, in case of a Francis turbine, we had a tail race which was straight. You can see that it is straight in the sense placed in this manner. But here, in case of a Kaplan turbine, you will see that the tail race is of L shape. Okay, so here you can see it is L shape, and the same concept holds good here. In order to avoid cavitation is where there is a shortage of water inside the turbine, and this shortage of water in the turbine can be avoided only if there is a lesser pressure here and a greater pressure here, so that water from the inlet at a high pressure will enter, and it will flow over the propeller blades, and then it is discharged through the tail race. So the tail race in case of a Kaplan turbine will be of L shape. Okay, so these are the various parts which were discussed, and again, I'll be putting a animated or a video of a Kaplan turbine, which will further clarify the working of a Kaplan turbine. So this was the explanation which I just gave. So the parts are similar to that of a Francis turbine, except the runner. Runner is that propeller, and the draft tube. The draft tube, as I said, is of L shape in case of a Kaplan turbine. There is another difference, that is the Francis turbine is normally a horizontal axis turbine, while a Kaplan turbine is a vertical axis. Hence, the front view of a Francis turbine resembles the top view of a Kaplan turbine. I also mentioned that the runner resembles the propeller of a ship, and hence Kaplan turbine is also called as a propeller turbine. But in all the three cases, finally when the shaft starts rotating, the shaft has to be coupled with the shaft of a generator in order to produce electricity. So this is the working of a Kaplan turbine. That is what, we have the draft tube, which is L shape, and it is also this also needs to be always immersed in the tail race to ensure that there is a kind of a suction effect, so that the turbine is always filled with water. Now, coming to the last part of our discussion, we need to discuss or understand what are the differences between impulse turbine and reaction turbine. Now, in an impulse turbine, the whole of pressure energy is converted into kinetic energy. That is, the potential energy is converted into kinetic energy. Whereas in a reaction turbine, it is a combination of both. You have both pressure energy as well as kinetic energy as the water moves over the moving blades. Then in an impulse turbine, the pressure of the water will be the same, that is the atmospheric pressure. But in case of a reaction turbine, the pressure continuously decreases as the water moves over the blades. That is what is mentioned here. The pressure decreases as the water flows over the moving blades. Then in an impulse turbine, the impulsive force sets up the rotation of the turbine wheel, whereas in a reaction turbine, it is a combination of the impulsive force and the reactive force which rotates the turbine wheel. In the impulse turbine, water is admitted only over a portion. What it means is, if you carefully observe a Pelton wheel, the nozzle of a Pelton wheel through which the water comes out at any given point of time is going to hit only one bucket of the Pelton wheel. While in case of Francis turbine and Kaplan turbine, the entire casing is filled with water, and water is flowing through all the blades or flowing over all the blades. So water may be admitted only over a portion of the circumference. Only there is one nozzle which comes. Whereas in case of a reaction turbine, water must be admitted over the entire circumference of the wheel. Then in an impulse turbine, water is discharged directly from the turbine wheel to the tail race. So it enters at atmospheric pressure, and it is discharged also at atmospheric pressure in case of a impulse turbine, that is a Pelton wheel. But in a reaction turbine, water is discharged into the tail race through a draft tube. Draft tube is a diverging section pipe, which can be either having a rectangular cross section or it can have a conical cross section, but it has to be diverging. This is to ensure that as water flows, there is a further decrease in the pressure, so a differential pressure is set up, and there is a kind of a suction which is created, because the casing in case of Francis turbine and the Kaplan turbine should always be filled with water. So these are the differences between impulse turbine and reaction turbine. So that completes the discussion on Francis turbine and Kaplan turbine. Thank you very much. And it also completes the discussion on this particular module. We'll be starting with the next module from the next class. Thank you.